Hello guys, today in this video we are going to discuss about Planck's radiation formula. The explanation of black body radiations came from the German physicist named Max Planck in 1900. Okay, and he gave few postulates. Based on that, actually the Planck's radiation formula was derived. So the first thing he said is the radiation field in a uniform temperature enclosure remains in a state of dynamic equilibrium. So if you have a enclosed container like this, okay, and where the temperature distribution throughout this enclosure is constant, right, a uniform temperature, right, so still at this constant temperature the system is actually in dynamic equilibrium. So the system is said to be in a dynamic equilibrium. Okay, so what do you mean by dynamic equilibrium? Though the equilibrium condition is there, that means the temperature is uniform. Okay, still the process of emission and absorption constantly happens, right? That's why we say dynamic equilibrium, right? So for this to take place, and at the same time, you need to consider equilibrium, that the temperature is constant, and dynamic equilibrium, as we said, state of dynamic equilibrium, as emission and absorption continuously happening. Okay, so what he assumed here, the presence of harmonic oscillators. So he considered harmonic oscillators lined up along this wall of the enclosure. Okay, so this wall, is like kind of, harmonic oscillators, these molecules or whatever you consider in the enclosure, the walls. Okay, they are all like, harmonic oscillators, you consider this way, these harmonic oscillators. Okay, so first thing that was assumed in this particular model is this, right? And these particular harmonic oscillators, they absorb energy from the radiation field and give it back to the field. Okay, so any such oscillator does not radiate energy until its energy reaches an integral multiple of a certain minimum. Okay, and that certain minimum we called a quantum of energy, certain minimum, that is known as the of energy quantum of energy. Okay, and this quantum of energy, that minimum energy, certain minimum energy, that will be absorbed from the radiation field by the oscillator, or will given it back to the field. Okay, is a certain minimum energy given by quantum of energy, and this quantum of energy is actually proportional to the frequency of this oscillator, harmonic oscillators. Okay, so what we said, the energy of this energy, this minimum energy or quantum of energy, is proportional to the frequency of the oscillator. Okay, that's the first postulate we said. And the second one, we will say that an oscillator absorbs energy from the radiation field, okay, and delivers it back or gives it back to the field in the quanta of, in the, certain minimum value, that is given as 0, or we can write E, or you can write 2E, so on, right? Where this E is actually is the quantum of energy. Okay, or we said that certain minimum energy, that is, in terms of that, as a multiple of that amount of certain minimum, okay, the energy will be absorbed or given back by the oscillator. Okay, so simply we said this energy is actually proportional to nu, or the frequency. Here I said nu is frequency and this is the certain minimum energy, or you can write this E is equal to h nu. Okay, this way we can write, where this h is known as the Planck's constant, given by 6.626 into 10 to the power minus 34 joule second. Okay, this is the value. Sometime also we use this as a constant, h bar or h cross we call it, as given by h by 2 pi, and the value, if you will substitute 6.626 into the minus 34 divided by 2 pi, it will give you around 1.05 46 into 10 to the power minus 34 joule second. If you want to write, and another important constant that is always used, h multiplied with c is the speed of light. Here h is the Planck's constant, is also a standard value. As h is a constant, c is also a constant. It gives you 12400 in terms of electron volt and angstrom. Okay, so this is the unit. So these are widely used constants, okay, in quantum mechanics, okay, in a quantum scale. Well, so the third postulate that we are going to, so this is what we said, the second one, okay, and the third postulate that we will say is the number of oscillators, such harmonic oscillators that we said, that are there in the enclosing wall of the container. Okay, so the number of oscillators emitting particular energy, okay, they follow Maxwell Boltzmann distribution law. So oscillators, these harmonic oscillators, they follow Maxwell Boltzmann distribution law. So let us discuss what is that. Okay, if capital N here is the total number of harmonic oscillators, okay, total number of harmonic oscillators, okay, and capital E, suppose, is the total energy of all these harmonic oscillators, right? And if you want to find out the average energy, right, the energy per oscillator, if you want to find out, then let us write this way: energy per oscillator, which will be given by total energy capital E divided by N. That way we can write. Okay, so this is what. And if I will take, like, n0, n1, n2, okay, these are, like, for nr, suppose, okay, these are the number of oscillators, okay, are the number of oscillators with energy values 0, E, 2E, 3E, okay, like this, okay, up to, E, okay, respectively. When I said respectively, that means what? So we have total n number of oscillators, so in which you have n0 number of oscillators with energy 0, n1 number of oscillators with energy E, n2 number of oscillators with energy 2E, n3 number of oscillators with energy 3, likewise. Okay, so this way, if it is the distribution, okay, and nr number of oscillators with, sorry, er, and so on, right, so on. So these are the, number of oscillators with this value of energy respectively, we said, right? So that I can write what is the total number of oscillators. Now total number of oscillators, I will add these oscillators n0, n1, n2, so all these numbers can be added. So n0, n1, okay, n2, plus up to, plus nr, and then whatever number of oscillators, n number of oscillators, you can write by just adding these. Similarly, total energy, if you want to write, so we said n0 number of oscillators are having energy is 0, so total energy will be n0 times 0, that gives us 0, plus n1 number of oscillators having energy E here, right? So you can write, like, n1 times E, that will be the value. Similarly, n2 number of oscillators are having energy 2E, so n2 number of oscillators having energy 2E, so you can multiply this. So this way you just keep on adding for all these values. Similarly, for R, if you want to write, then you have nr times er, right? So that will be the total energy, which is E, right? So total number of oscillators and the total energy can be written this way. Let me just rewrite this again. So we said n equals to n0 plus n1 plus n2, okay, plus up to plus nr, and then further whatever number of oscillators. And total energy E is given by 0 plus E times n1 plus 2E times n2 plus 3 times n3 plus re times nr plus dot dot. Okay, so on, right? Now, according to Maxwell-Boltzmann distribution law, the number of oscillators with energy Re. Okay, so if you had to write number of oscillators, with energy Re, okay, is given by, as per Maxwell-Boltzmann distribution law, Nr, if I'll write number of oscillators with energy Re, it is given by N0. This is the distribution, Maxwell-Boltzmann distribution that we are writing, Re divided by Kt, right? So from this distribution law, we can further find out the Planck's radiation formula using this distribution. Nr is equal to N0 e to the power minus Re by Kt. So here you can see this K represents the Boltzmann constant. This is the Boltzmann constant, which is given by 1.38 into 10 to the power minus 23 joule per Kelvin, right? Or else we can write in different unit, 8.62 into 10 to the power minus 5 electron volt per Kelvin, if you want to write. Okay, 1 electron volt, 1.6 into minus 19. Okay, so that can be multiplied with this, right? So we got the Boltzmann distribution. So number of oscillators with energy Re is given by Nr is equal to N0 e to the power minus Re by Kt as per the distribution law, right? Now let us write all the values, like what is N1 in terms of N0, N2 in terms of N0, okay? So on and so forth we can write, and then we can substitute here for N, right? So the next step that we are going to do is, using that distribution function in mind, Nr is equal to N0 e to the power minus Re by Kt. You can write it for N1, which is N0 e to the power minus E by Kt, right? Similarly, you can write for N2, which is given by N0 e to the power minus 2E by Kt, okay, and then 3 as N0 e to the power minus 3E by Kt, right? So on, right? And then substitute these values here in N, which is N0 plus N1. We can substitute N0 e to the power minus, sorry, E by Kt, plus N2, which is N0 e to the power minus 2E by Kt, plus up to this way. And for R term, if you are writing, plus N0 e to the power minus R times E by Kt, right? Plus up to. Okay, so here you can see N0 is the term that can be taken outside. Okay, you can see in every term you have this N0 value. You can take this out so that we can rewrite it. So the total number of oscillator is given by N0, and we can write 1 plus e to the power minus E by Kt plus e to the power minus 2E by Kt plus up to the rth term, if I write e to the power minus Re by Kt plus, right? So this way you can write, this implies we can write this to be N, and this is N0. Okay, here you can see this is in the form of a series where you are multiplying, you can see 1, then you multiply d to the power minus E by Kt. Okay, so you got this, and then again you multiply d to the power minus E by Kt, that gives you e to the power minus E by Kt. So this way you can see it's in the form of a geometric progression, so you can write that. Okay, this way we can write 1 minus e to the power minus E by Kt. So 1 by 1 minus R we got, right? So this is what we got for total number of oscillators. Same way we can write for the energy. Energy is similarly, you got N0 times 0, that is the first term is 0 plus E times N1, which is N0 e to the power minus E by Kt. Then you have 2E times N2, which is n0 e to the power minus 2e by kt, right? So go on, and then plus re e to the power minus re by kt, and then continue, right? So here you can see, forget about this 0, you have en0, that is common. You can see en0 in all these terms, right? So take that outside. So en0, if I'll take out, and this e to the power minus e by kt as well, right? E to the power minus e by kt. So especially the first term is common everywhere, right? So you take that out, what we got is 1 plus 2 times e to the power minus e by kt, right? Plus 3 times e to the power minus 2e by kt, so on, plus r e to the power minus, here if you take e to the power minus e by kt, you got r minus 1, right? And then you have e by kt, right? So as it is, okay, then plus continue, right? This way we got. So now you see here what you got, this is in the form of kind of, you can see 1 plus, suppose this is 2x plus, you can see 3x square plus, you can see, like, 4x cube. So this way if you'll see the series, it gives something like this. So 1 plus 2x plus 3x square plus 4x cube, likewise. So if you'll write this series, we can actually write it as 1 minus x to the power minus 2, right? So here this way we can write, and then you expand it, you can write this way, and this, the series can be written this way, okay? So substituting this thing, 1 minus x to the power minus 2, where your x is actually what, x is given by your minus e to the power minus e by kt, right? Here x is equal to, here x I took minus e to the power minus e by kt, right? So let us rewrite it again. So this total energy can be written as E times n0 e to the power minus e by kt, which you took common. And here I wrote 1 minus x. X is our e to the power minus e to the power minus e by kt, right? To the power minus 2, right? Which can be written as e times n0 e to the power minus e by kt divided by, you just write it as a positive value, minus e by kt positive, this square, right? You got this way. So now if you want to write out the energy per oscillator, which is E bar is equal to actually E divided by N. So whatever E value just now we got, that is E n0 e to the power minus E by kt divided by 1 minus e to the power minus E by kt whole square, okay, multiplied with this 1 by n, that gives us 1 minus e to the power minus e by kt, that we have already determined the value for n, okay, this divided by n0. Then you cancel whatever can be cancelled out. So you can see this 1 minus e to the power minus e by kt, and here you got a square, so you can cancel this, you can cancel this n0 with this n0, right? And write the remaining value. So we got E bar, that is the energy per oscillator. If you want to find out, that gives you E to the power E multiplied with exponential to the power minus E by kt, right? Divided by 1 minus E to the power minus E by kt as E by kt, right? So that gives you the average energy here. Average energy means energy per oscillator that we calculated, okay? So now if you will say the number of oscillators per unit volume, okay, in the frequency range of nu and nu plus d nu. So in the frequency range of nu and nu plus d nu, the number of oscillators per unit volume, that is given as n is equal to, from solid state physics we can actually derive this, 8 pi nu square c cube divided by c cube d nu. Okay, this gives you what, the number of oscillators per unit volume in a frequency range nu and nu plus d nu. okay, or a frequency range of d nu. So in that frequency range d nu, the number of oscillators per unit volume present is given by 8 pi nu square by c cube d nu, right? So the average radiant energy, okay, radiant energy per unit volume in that frequency range d nu can be written as, suppose I will write it as E nu d nu. This gives you what? The average energy per unit volume in the range of d nu, okay, is given by n times, and then of course the energy per each oscillator, energy per oscillator. So it gives you what? Number of oscillators multiplied with what? The average energy or the energy per each oscillator, energy per oscillator. So that way, now we can substitute the value. So we got in the frequency range d nu, we have the number of oscillator value. So 8 pi nu square divided by c cube, okay, and d nu multiplied with the value of this E bar already we have calculated using the Maxwell-Boltzmann distribution law. So that is given by E to E multiplied with exponential of minus E by kt divided by 1 minus E to the power minus E by kt, right? So here we can rewrite it as 8 pi nu square, okay, and then h nu e to the power minus E by kt divided by c cube 1 minus E to the power minus E by kt d nu, right? So here we just substituted the value of E here, this E is h nu, substituted this, and then the whole thing we wrote, okay, fine. So now this can be further, you can simplify it, right? 8 pi nu square, you got nu, so that gives you nu cube. So 8 pi h nu cube d nu divided by, we got c cube into 1 minus E to the power, this E is again h nu, I substituted h nu by kt, right, for that E value, right? And then this whole thing, you got another multiplied with E is there. Yeah, so this is E to the power minus E by kt. Oh, I missed this one. E to the power minus E by kt is also there, right? So let us multiply that. E to the power h nu by kt, okay, minus E by kt, sorry, minus h nu by kt, right? And then you further simplify it, whatever here you can see E to the power h minus h nu by kt is multiplied actually here, okay, this is multiplied here in the numerator, okay, not in the denominator part. So let me just rewrite the final thing that we can write E nu d nu, okay, that is the average radiant energy per unit volume in the frequency range d nu is given by 8 pi h nu cube divided by c cube e to the power h nu by kt minus 1, right, and then d nu. So this is the value of energy, radiant energy in the frequency range of d nu, right? And this particular equation that we got here, okay, that gives you the radiant energy in the frequency range d nu. This is q because, okay, this equation is known as the Planck's radiation law, okay, or Planck's radiation equation. This is the equation that will give you the amount of energy, radiant energy per unit volume in the frequency range of nu and nu plus d nu. In terms of wavelength, if you want to write, then you know that nu is equal to c by lambda, and your d nu can be written as c by lambda square d lambda, and then you can substitute here, so that we can rewrite the same equation in terms of lambda, as E lambda d lambda is given by 8 pi h c cube, okay, divided by c cube e to the power h nu by kt minus 1, h nu by kt minus 1, okay, and then substitute all the values here. Okay, so you got lambda cube here, okay, nu is equal to c by lambda, we substitute, so nu cube is equal to c cube by lambda cube here you got, and d nu you got c by lambda square d lambda. So just simplify, cancel whatever you can cancel, and finally we can rewrite in terms of lambda. If you want to write, E lambda d lambda is equal to 8 pi hc divided by lambda to the power 5, and it is given by 1 by e to the power hc by kt minus 1 d lambda. Okay, this, and I don't, yeah, okay, this, and then we have d lambda. So in terms of wavelength you can write this way, and in terms of frequency you can write this way: E nu d nu is equal to 8 pi h nu cube divided by c cube e to the power h nu by kt, h nu by kt minus 1 d nu. Okay, so this equation in terms of wavelength and in terms of frequency can be written for Planck's radiation formula. Okay, so this actually gives you what the amount of radiant energy per unit volume in the wavelength range lambda to lambda plus d lambda, or in the frequency range nu and nu plus d nu. Okay, thank you for watching.